So far, so yeah, I really enjoying the stay here. So thank you for everything. So I'm going to talk about a little bit as the continuation of what Juan Carlos spoke in the morning. We are facing basically bi-level optimization problems related to image processing tasks. So this is the framework that I will be following. I think this is the laser print. Yeah. So I will start with some repetition of what we saw in the morning, early in the afternoon, and then I will go through some of the concepts that Juan Carlos went through, and then we will develop some theory, some applications on top of a finite dimensional space. So let's start. So the first task that I will be focusing on is the image denoising task. So it's a common task. It's one of the most popular, I think. You have a noisy image, and you want to reconstruct the original image out of the noisy one. So it's, well, as you saw in the morning, it's a nil-post problem. It has a lot of problems with the existence and different kind of other related problems. So what we have seen through the years is that we have been developing these variational models in order to solve this problem. These variational models are quite popular. This is one of the, the most popular ones use this total variation semi-norm, so as we saw in the morning. And this is the model that is most commonly used for this kind of task. These variational models, they use a trade-off. They always make a trade-off between a data term and a regularity term. And you have to pick that parameter wisely, because otherwise you can get wrong results, or you can get better results by changing a little bit. So you have to find a way for finding these parameters. So as we saw earlier, this is the model that we will be trying to solve. This is an infinite dimension version of this problem. So you have the data fidelity term that you have here. And then you have a regularity term, and then you have a sum of different kind of noises that we saw earlier in the morning, and you have a parameter for each kind of noise. So then you want to detect which one is the most representative for each image. So if we change the problem into an H01 set, you get something like this, which basically includes, is basically the same with this diffusion term over here, which is the one that we saw earlier. I will go through because you already have seen this. And now I will make the first step. I will be limiting this first problem to just the Gaussian noise. Just for purposes of experimentation, I will just choose the Gaussian noise, which is described by this data term. And then this formulation in H01 gave us this. So this is the formulation that we can work on, that we will be working on. So what I will do now is I will change this set into a finite dimension. And we can see that this is a variational inequality of the second kind. So you have a bi-level problem when this inequality becomes the constraints for the upper level. So you get optimization problems with a variational inequality of the second kind as a constraint. So this is basically the problem. If we translate this into a finite dimensional space, it will look something like this, where when over here you can see the Laplacian, the discretization basically of the Laplacian and the differential operators. And yeah, basically it will look something like this. So we have a problem that has like an energy minimization in the first layer, and then you have a variational inequality in the second layer. So that's the setup, and everything is done in finite dimensional space. So we want to see something here. We want to understand what's going on with this in terms of differentiability, because a common practice in this in this kind of problems is to use regularization in order to get these non-differentiable terms to become like some smoother, and you can characterize and joint and then get a gradient, and then you can implement numerical methods for this. So we will try to do the same but without a regularization technique. So this is one of the important parts. So in order to analyze the differentiability of this solution operator is going to be, first we start with a perturbed problem of the one that we saw before. Basically, we want to analyze the differentiability on the point lambda in a direction h. And we reach this result, which is quite interesting. We can see that indeed this operator is differentiable in finite dimensional space. If we can, and it basically, you can, this differential operator, it complies this VI of the first kind. So there when you have here, it's basically a sum over an active set, which is defined here, and an active set, which is defined here. So what we're doing here is basically making a characterization of the solution based whether if it is in an inactive set, which is defined here, and basically the solution is going to be inside of this K, which is a cone. It's a self-differential cone. We can characterize the cone like this afterwards. So if we characterize the cone like this, we can say that this cone is unique, and we can say that differential is unique as well. And because of that, we can make sure that this solution operator for this variational equality is going to be directional differentiable. So that's an important thing, because we will be using that for our numerical implementation. So for the numerical implementation, we will be using this kind of problem. So we already saw this. So we have like some sort of energy minimization here. We have a parameter which measures the similarity with the original image, and then we have a restriction over the parameter with a beta. This beta can be 0, it can be any value bigger than 0, and then you get some sort of restrictions over the values that lambda can get. So we will recall that this is the inactive set. Basically, we're taking where the values where the derivative, the gradient of the image u that we're inputting is 0. And then we get we can start characterizing this system, characterizing this optimal point. So basically, what we're saying here is that we get a linearized system, and in this system we can say that it follows a strict complementarity condition. So this strict complementarity condition says that this set is basically null. So there's no something like that. So it's empty, or it is actually very small. So when we get this, we can say that the strict complementarity condition holds. And then we can see that these linearized systems properties are held. And with this linearized system, we can derive a complementary adjoint. So this is the step that allows us to get a characterization for the adjoint, and then we can implement this adjoint numerically. And with that joint already calculated, we can actually get a derivative candidate. And with this derivative candidate, we can actually implement this trust region algorithm. What this trust region algorithms is basically a minimization algorithm that actually tries to fit a quadratic model. So you get a point and you try to get a quadratic model, and you gotta take a measure of how good it is. And in that, there's defined a radius. So if the approximation is good, you get a bigger radius. If the approximation is bad, you get a smaller radius. And then that's the radius that you work within the context of optimization. So this is the quality indicator. So if you define this array and this breadth as these values over here, you can get the quality indicator like this. So this quality indicator will tell me if you have a bigger radius or a slower radius, and then you can start defining your zone where to look for the optimizer. So we did implement this numerically. We solved the lower level, the variational inequality we saw before with the semi-smooth Newton method. And we implemented the trust region method with the adjoint that we showed previously and the gradient that we showed previously. And we saw something like this. So we have first stage, we have a noise with a sigma 002, a Gaussian noise, obviously. And you can see that we could see that we reached optimal parameter. In this case, it was just one kind of noise, and this noise was a Gaussian, and the parameter was this one. And we can show the cost function. So we can see it actually reached to the minimum 16 iterations, which is super fast. I mean, for this kind of environments, it's a fast kind of approximation. And we can see the residue as well. We are calculating the residue as the difference between the real function and the quadratic approximation. So we can see that, So we can see that it gets bigger at some point. It means like the radius gets bigger at iterations 20, and then it starts shrinking down. It means that it's really close to the minimum, and then after 30 iterations or so, it's already in. It's already close to the optimal solution. We increased the size of the noise, and we could still get an optimal parameter. And we could see this kind of behaviors on the cost function, and the same as the residue. And we can see here, this is the optimal parameter for lambda. We can see that it actually, after 20 iterations, it actually gets closer to the minimum, and it gets like doing minimum refinements over there. And as a final remark, as I'm running out of time, and we are using a different approach for handling this non-differentiable term. We are using, instead of using a regularization technique, we're taking advantage of the differentiability of this solution operator, which we can prove in finite dimension. So when we work in finite dimension, we can prove this differentiability, and we can use this differentiability in order to get optimality conditions. So we don't need to regularize. So that's a good approach. And as we saw earlier, I mean, we can guarantee this in the context of an inactive set. I mean, when the strict complementarity conditions hold. So we need so that's why normal numerical methods doesn't work that well, because the direction is not necessarily a descent direction, because it basically has to be an element of the self-differential, and it's not guaranteed that. So that's why we choose trust regions methods for this, because we can make mistakes. So when we make mistakes, you just basically get a bigger radius, and then we can perform better under mistakes, and we can get better at the next iteration and next iteration. So it's proved that it works well in practice, and the iterates are getting robust. So thank you very much for your time. So that's good.
We have time for a short.
So this is I joint work with Camilo Hernandez, which is my PhD student at the Universidad de los Andes, the math department. So I'm going to talk about the Finetis problem, the Finetis optimal dividend problem, but with a constraint in the time of ruin. So let me start with the outline. So first, I'm going to define what is the Finetis problem, which is a very old problem from the actuarial sciences. Then I'm going to tell you what is the problem that I'm trying to solve, which has a constraint on the time of ruin. I'm going to talk about the dual problem, a few words about the exponential claim case, which has been already published, and an extension that we already have for spectrally negative Levy processes, numerical examples, and some extensions and future work. So first of all, what is Definitis problem? So we have an agent, let's say an insurance company. So this insurance company has a reserve process that I call X. For example, something like this. And we have claims that are modeled like negative jumps. For example, like these things. So we have this reserve process X. And we have a dividend process D, which is the cumulative payments that the company makes through the time. This is an adapted, non-negative, non-decreasing Cadillac process, starting at 0, adapted to the filtration generated by X. And if we have X minus D, we have the surplus process. And we don't allow the dividend process to lead to ruin the reserve process. So that's this condition. So we have theta, the set of strategies that don't allow ruin, don't lead to ruin. So the objective function is to maximize the flow of discounted dividend payments throughout the time until the time of ruin, which is this tau d that depends on the strategy. I'm using here Q because I'm going to use QSCAL functions like Daniel did before. So the Definitis problem is just find what is the best strategy for dividend payments. And this is very old. And for some processes, there is a book by Schmidli that summarizes all the techniques used to solve this problem. And later, we have this work by Loffen that extend to the spectrally negative Levy process that I'm going to talk about later. So what is the motivation of imposing this constraint? There is a trade-off between the stability of the company and the profitability of the company. If we want to minimize, for example, the ruin probability, then that will lead that we don't pay any dividend. But if we maximize the dividends payment, then we will have a certain ruin. So the idea is to balance this trade-off, imposing a constraint. Some related work in this direction is this work by Paulsen, Tauhausen, and Albuquerque. This is going to be important for us. Also Loffen and Renault. So the actual problem that we want to solve is this. We want to maximize the present value of the dividend payments subject to this constraint. So the idea of this constraint is that maybe I want the company to live at least a certain amount of time. So this is the meaning of this T. So this is the problem that we want to solve. So the idea is to use a Lagrangian relaxation to take the constraint into the objective function with a Lagrangian multiplier. So we have that the original problem is going to be the sup, the inf of this Lagrangian function. That's easy. And we have the dual problem, which is just changing inf with sup. We always have this inequality already. So the goal is to prove that there is no duality gap, that we actually have zero duality gap. So we're going to focus on solving this problem, which is the auxiliary problem, which is now a standard control problem. So we want to find how is this problem, so what is the solution of this problem, and trying to use it to prove that there is no duality gap for our original problem. So we started with a simple scenario, which is the case of the Cranberg-Lumber model, which is basically a compound Poisson process with a positive drift with exponential claims. So that's the Cranberg-Lumber model. And we were able to prove that there is no duality gap. And in fact, the value of our problem is just the infimum over all Lagrange multipliers of this auxiliary problem. And the key point there was the simple strategy that Daniel was talking about earlier. So we have barrier strategy are optimal for this problem. So we thought that maybe in a more general context, we have also barrier strategy, and that's the context of spectrally negative Levy processes. So this is basically what Daniel had earlier. So a spectrally negative process is a Levy process, which measure is supported only on the negative side and has no monotone paths, almost surely. So we are not allowing like subordinators. We have the Laplace exponent, and we also have the Q-scale function that Daniel was talking earlier. So I think I'm going to skip that. And we also have these sig functions which are defined in terms of the Q-scale functions. So why? Because, as Daniel mentioned, so we have the theory of excursion theory, and we have these reflected processes. So if I choose a barrier strategy level B, then the dividend process is going to be just the maximum of B and the running maximum of X minus B. So the surplus process with this strategy is going to be this, and this is basically just reflection in this barrier. So so we have a lot of theory for this reflection process. And so, for example, we can write the objective function in terms of the Q-scale function. That's one thing. And the other thing is that we can also write, so we have this property, this identity from Abram and co-authors that we can use to write the left-hand side of our constraint in terms also of Q-scale functions. So if we combine all this together, Laufen did, so we have that if I choose a barrier strategy at level B, then the Lagrangian function for that strategy is just this in terms, and everything is in terms of the Q-scale function. And if I want to optimize over this set of strategies, I just need to optimize over B, which only appears here. So basically, that's how you get what is the best barrier strategy, and then you use a verification lemma to prove that this is actually the optimal strategy. So we take this part that I'm calling here zeta lambda, and you just take the maximum of this. And for the case when the Levy measure is complete monotone density, has a complete monotone density, like most of the cases, like for example, alpha stable process has this property. So we have that this function has a unique maximum, and that's going to be the optimal strategy. So this is the definition of a complete monotone function, and some examples. So Laufen proved what is the strategy for the auxiliary problem. So under some conditions, the optimal strategy is take the money and run, which is just pay everything out in dividends. Otherwise, there is going to be an optimal level given by this formula, or the maximum of this is going to be. So that is useful for us because then we have a way to, given a B in this set, this B star is going to be the level of the definitist problem without any constraint, this B0 star. So if we have a B here, then I can map this B to a lambda so that the level B is optimal for the auxiliary problem with that lambda. And that basically what allows us to have a certificate for optimality. Then we have this B star, this lambda star, and we can prove, for example, complementary slackness condition. And that's what we did. And basically, the proof, so we have the analog theorem for this case, that we don't have duality gap, and the value function of this constraint problem is just the infimum over lambdas over the auxiliary problem. And the idea is, so we define this function C, which is just the left-hand side of our constraint, and we try to find certificates for strong duality, B star and lambda star. We divide in 4 cases. So if I take an x, so note that here x is fixed. So I start with an initial capital X, and I also have a t, which is the parameter of the right-hand side of the constraint. So given x and t, I can find what is x here, what is kt, and find the point where these two lines intersect. For example, if they intersect in this region, that means that the constraint is not active. So the strategy without constraint is optimal. If they are in this region, that means that there exists a unique b, such that this function phi sub b, which is something like this, goes through that point. That means that the constraint is active. If I'm in this region, that means that the problem is infeasible, because the initial capital is too small, and the constraint is too hard to fulfill. So if we are in this region, the problem is infeasible. And if we are in this borderline, then we have that the optimal strategy is do nothing, but we are still feasible. So analyzing all these 4 cases, we have the proof for the theorem. So as a numerical example, I'm going to take the X as a Levy process with gamma, the positive drift 10, for example, a diffusion term 0.1, and this is going to be the Levy measure, which is basically this is telling us this is a 0.8 stable process with diffusion. And for that case, so this is how the function phi c sub b behaves. So for example, if I'm in this point, this is the blue line is the line corresponding to the level without constraint. So if I'm in this point, the constraint is not active. If I'm in this point, so there is a unique line here that goes through this point. So that's the B star that is the optimal strategy. So these are the cases. The other cases, I don't show it. These are the values for the axillary problem for these cases. So in this case, when the constraint is not active, so the minimum is at lambda 0, so that means that the constraint is not active. If in the other case, this function b lambda is always a convex function on lambda because it's the dual function. So we have a unique minimum here in this case. And these are the value functions for different right-hand side. So the blue line is the value function without the constraint. If t is a little bit bigger, then so this is going to be the value function. And here, for example, this is not that the value function is 0. It is in this region the problem is infeasible. So so only makes sense for x to be only from this point on to have a finite solution. So some extensions we can we are working now in the dual model, in which in this case the process is an spectrally positive Levy process. So we have a negative drift and jumps upwards. We can try to do something similar when we have a fixed transaction cost. In this case, it's proven that the optimal strategy is a band strategy. So if we are below some level, we take the if we are below some, if we are in some level, we take the dividends down. But then I don't have only one parameter. I have 2 parameters, 2 levels, two values of b. So then we have to do some work to prove a similar theorem, and also try to extend some more maybe realistic constraint like this. This would be a constraint like more natural than we imposed, or something like this kind, which seems harder to deal with. So these are some references. This is where many of the identities for the spectral, the QSCAL functions, you can find many of these identities. And this is the paper where we published the results for the exponential claims. And I think that's it. Thank you.
Questions or remarks?